Video, we address the learning objective A and C and apply that in problem 2 of today's class. For the next lesson video, we determine the desired load for the lateral braces or strut and design lateral bracings for goals and column forms. So let's get to the design load. So for the design for lateral bracings and strut, or also called brace load, and that to determine the load strut load per foot of the form, and that P apostrophe based on this equation, P apostrophe equal to H capital uppercase times H lowercase times L divided by H apostrophe L apostrophe, and the units equal to pound per linear foot of the form, and L equal to square root of H apostrophe square plus L apostrophe square. And in this case, H is the lateral load at the top of the form, and that can be determined available in slide that you have here. The minimum lateral design load for the goal forms, and it depends on the goal height, H small, if it's less than 8 feet, or between 8 and 12, or more than 12 feet height. And the equation available, as you can see here, design lateral force applied at the top of the form in pounds per foot or kilonewton per meter. So that is H capital. H small is height of the form, and H apostrophe is the height of the top of the strut, and then L length of the strut, L apostrophe the horizontal distance from the form to the bottom of the strut. So let's go to the back to the slide that we discussed in the first lesson video of today's lesson. So the strut is the brace, as you can see, and with that, what is the S small? So from that is the goal, the height of the goal. So from here to the top, S apostrophe from the top of strut to the goal form, S apostrophe, and L apostrophe from the goal form to the bottom of the strut. So that horizontal distance, and L is the strut's distance. In this case, make more visual. This is L apostrophe, S apostrophe, and this is H from top to bottom. And the brace are struts, so that we can be able to go back to the node, and that we can determine strut load per foot of the form, pound per foot. And then from that, we can determine the total load per strut, that is per linear foot of the form. It will determine by P apostrophe at determined in previous equation, and then we can apply strut spacing. Or we know the total load per strut, then we can determine strut spacing. So with that equation, we can do either way. In the next problem, in the problem 2, on the next video, it will determine the strut spacing based on this equation. And of course, as you can see, the strut or the brace can be in buckle, because can be in compression for the lateral strut. So to consider that buckling, we also need to adjust, and that is the maximum allowable load on the rectangle wood columns, and that is FC. And if you recall, FC is the allowable stress for in compression. Allowable stress in compression. FC apostrophe, we adjust for the buckling, and that equation, just remember, in mechanics of material, columns we determine buckling, and that is earlier equation. Similar to that, we can have here 0.3 for the wood, 0.3 times E modulus of elasticity divided by L over D, that is the ratio of the length of the strut or brace over the smallest cross section dimension of the cross section, D, L over D square, and have to be less than FC, which is allowable compression in stress. Allowable stress in compression, FC. allowable unit stress in compression and parallel to the grain, and adjustment for the L over D ratio, as I mentioned earlier, it depends on how slender of the member is, in this case how slender or braced or struck, and that L over D have to be less than 50. If it's more than 50, it's too slender. It should not work. It's easy to buckle. So keep that in mind when you design. You have to check it less than 50. Make sense in that? And what it be a compression that parallel to grain or perpendicular to the grain. If you recall, that is the finger that I discussed in the previous lesson video. In this case, the grain go east-west, and the support, the joint, go south-north. So you can see that in this case, it is the grain perpendicular to support. This finger, the grain parallel to the support. So with that one, in the next lesson video, you will apply the lateral design support for problem 2.